we are going to assume that we have this memory block. This is our memory block, and we are going to assume that every row or the addressability of this memory is a byte. So, it is going to be a byte addressable memory, where every row is going to have uh, 8 bits or a byte. So, 8 bits, okay, and the total number of such rows, or the total number of bytes that are going to be contained in the memory block, we are going to assume something. Typically, we can start with something very simple. It could have, let's say, just 16 such rows, right. So, we just using 4-bit address, we can refer to each one of these bytes, right. So, for the start, we can start with let us say this is memory location 0x1, 0x0, 0x1 and so on, and it is going to go to 0xf, which is a total of 16 bytes. Okay. So, this is we will keep in mind, and the programs that we are going to develop, which is going to run on our processor, is going to assume this constrained design. Of course, in this because of in the interest of time, we cannot design something which is super complicated, but I am trying to give you a high level idea of even how to do a simple processor design like this. This is also going to be very inefficient, but at least you will get the high level idea and the basic principles of the functioning of a processor. Okay. So, this is about the memory block. Then as I kind of told you here, this memory block is going to be issued an address, and this address is going to be 4 bits long. Okay. So, the address is going to be 4 bits long because you have 16 locations. You have to refer to one of the memory location using 4 bits. 2 to the power 4 is 16, and whatever comes out of the memory block, like the value that comes out, this could either be part of the program, because we are storing both data as well as program in the same memory block, right. So, it could either be part of the program, which is an instruction. It could either be an instruction, or it could also be data, right. So, you need to keep in mind that both of them are stored in memory. Okay. So, when a program is being run, typically it is going to execute instructions, right, and as a part of some instructions, data might be referenced from the memory and data has to be fetched. In that case, you have to go back when you do add x5. When I understand that, when the processor understands that add is the instruction that it is going to execute, then it sees this value 0x5, and it then understands that it has to fetch the value that is present in the memory location 5. So, then again it is going to issue the address to the memory, which is 0101, which is 5, and the value that is going to come out of the memory is the data that the processor is looking for performing the add operation. Okay. So, this is what we have to tell about memory. Now, we will develop a mechanism such that all this address goes to the memory block, the value is looked up and the value is sent to the processor, and the processor kind of takes these values and does the computation. So, if I look at the high level picture of the CPU or the processor, right, let us say this is our CPU or the processor. I am going to go into details, but I am going to first giving a high level pitch of how the rest of the design is going to be structured, so that it is easier for you to follow. So, the processor is going to be, of course, connected to this memory, right. And as I told you, so it is bidirectional. So, you do not just only load from the memory, but also whenever you have done some computation, the computed value might have to be stored back to the memory location. So, that is the reason I have this arrow which has two heads, right. So, this is bidirectional. You have to both uh, load from memory. So, this is something you have to load from memory, which is loading to the CPU, or you might have to store. So, store is from the CPU to the memory, right. So, you compute 8 plus 4, the result is 12, but there is no point in having the value 12 stored in an internal register of the CPU, right. How will people read that, right. This value has to go back to the memory and then probably displayed and so on, right. So, also you can have input output devices, that is not something that I may have a lot of time to discuss, but you can think input output devices also act as memory blocks, right, where if you write to a particular memory block, that is going to be displayed in a screen, right, or printed by a printer. Similarly, you can have, let us say, keyboard, which is an input device. When you type something on the keyboard, this is going to write to a very specific location inside the memory, and the CPU is going to read from the same memory. So, IO could also be a kind of thought of it is a memory operation, and the input output device is going to write to this dedicated memory. Okay, I am not going to discuss input output devices in detail, but once you understand how the CPU interacts with the memory block, this is similar, right. One portion of the memory block is going to be dedicated for the input output devices. It could be display, it could be keyboard, it could be mouse, it could be a printer, it could be a network device. Basically, CPU only sees the entire world as memory locations. Whatever is inside the CPU are registers, whatever is outside the CPU, it basically talks to the memory blocks. And how you classify the memory blocks into various kinds of let us say hierarchies, or certain portions of the memory could be privileged, certain portions of the memory could be used for some secure operations, right. That all these kind of classifications are kind of done separately. Okay, it could be done by the operating system, right. I am not going to go into that discussion further. So, let us look into the CPU, and CPU is going to contain, as I told you, a set of registers. Okay. So, this is a set of registers, okay, and the collection of this set of registers is often called a register file. What is this going to be used for? This is going to be used for temporary storage, right. Whatever program that you are writing may require a lot of local variables, and you do not want to have the local variables always stored in the memory and then fetched to the CPU, you do some computation, again it is stored in the memory. This is time consuming, because whenever you have memory intensive operation, it tends to take more time. Rather than that, if you have the values locally available to the computational circuits in the particularly in the registers, it is much faster. Okay. So, here you have the computational elements. Typically this circuit is called ALU, which stands for arithmetic and logical unit. Okay. So, this is something that I was kind of referring to when I spoke about this various operations being supported inside the CPU, like addition, subtraction, multiplication, or logical operations like shift, or let us say complement, XOR, and so on. So, you pass operands and the ALU is going to act on those operands, right. So, often the ALU is going to be connected to uh, two registers. It could be two dedicated registers, or those registers could be a part of the register file, right. So, it could be one operand, right. So, you can say source SRC operand 1, you can have another one which is another source operand. It is optional because not every operation is going to require two operands. For example, if you do not of x, there is nothing, no role of a second operand, right. So, it is going to vary from instruction to instruction. So, operand 2, right. And similarly, for writing back the results, you can also have a destination operand, destination register. Okay. So, source operand 1 is nothing but like source register 1, source register 2, and while you write back the result, it is going to go to a destination register. Destination register could also be one of the source registers, right. That is again up to the CPU designer who decides what exactly to do about it. Okay. So, it or you can always have the have an implicit definition that it is always going, the result is always going to be written to the accumulator. Okay. Why I am mentioning this is all this information that you are saying that okay, operand 1 is like one register, operand 2 is another register, the destination is another register, and then you also have to convey the fact that let us say this is an addition operation. All this information has to be encoded inside the instruction, right, because add is basically a human perceivable term, right. When you write the program in machine language, there is nothing called add, right. This is a going to be encoded in a binary form, right, which the processor is going to interpret as add. Okay. So, if you have let us say 15 or 16 different instructions, you can encode them by let us say 4 bits, right, 2 to the power 4. So, you can have add, subtract, or, and, XOR, and a series of them, right. They can be encoded using 4 bits, but you also have to reserve some bits for mentioning what register is the source register 1, what register is the source register 2, which one is the destination register, and so on. So, even if you can do a very simple calculation, right. Suppose you have 8 registers, right. Let us say you have 8 such registers, right. If you have 8 registers, then each register is identified by 3 bits, right. 2 to the power 3 is 8. Suppose I want to specify that I want to take the content of this register, which is the register number 0 and register number let us say 5, and put the result in register number 7. Okay. This could be the case, right. So, if I want to have the instruction which explicitly specifies so much, right, I have to spend or encode that information using the required number of bits, right. So, here I am basically telling source register 1, source register 2 and destination register. So, 3 registers. So, each register takes 3 bits to be identified, right. So, if I have 3 such registers, I will require 3 into 3 9 bits, right. So, let me kind of write it here just to kind of give you an idea about how the instruction is going to be encoded. So, here I have 2 to the power 3, so is equal to 8. So, 3 bits to identify a register. Now, if I have an instruction which looks like this, let us say some operation which is let us say add, right. You have a source register 1. So, I will write source SRC 1, then you have a source 2 SRC 2, and then you have a destination register DST, right. So, as I told you, 3 bits to identify a particular register. So, let us try to understand how many bits will be required to express this particular instruction. So, 3 goes here, 3 goes here, 3 goes here. So, 9 bits are done, right. And as I told you, I may have, let us say in our processor, let us say 15 instructions, right, or 16 instructions rather. So, if there are 16 instructions, you have to have at least 4 bits to identify which instruction we are talking about, right. So, let us say add is the 5th instruction in my instruction set. If there are totally 16 instructions, the 5th one is add, right. So, the 5th one could be just 0th one, first one, second one, dot dot dot, or 5th one. So, this will also require 4 bits to be expressed. Okay. So, as you can see 9 plus 4, 13, you require 13 bits to encode an instruction called add src1 src2 comma destination. There is a lot of assumption here. The assumption is that you have this many instructions and this many registers inside, right. If you have, let us say 32 registers inside, I need 5 bits to specify a particular register, right. So, just for expressing the fact that SRC1, SRC2 and DST, I need 5 plus 5 plus 5, 15 bits, right, because 2 to the power 5 is 32. Here I have 8 registers, so I need 3 bits. Okay. So, now you can understand why giving more flexibility inside the instruction itself also is expensive in terms of encoding the information that is contained in the instruction. Okay. So, if I rather say that I will not have a separate destination register, so this flexibility is going to be gone, but I am always going to say that the value is going to be available in a default register, and the default register could either be SRC1 or it could be an accumulator, which is not neither SRC1 neither nor SRC2, but this information is not passed from an instruction perspective. The instruction does not explicitly specify where the value that is going to be computed is going to be stored. The destination register is implicit, okay, not explicit. In that case, of course, I do not have to save these 3 bits. Okay. So, there is a trade off which is very important to understand. Any design, as I told you in the beginning of the semester, that there is a trade off, right. If I want to make my instruction set very flexible, right, I can control, I have a lot of tuning knobs, I have a lot of flexibility in my program, then you need to probably spend more on the number of bits that are used to encode instructions, and also the underlying hardware is going to become increasingly complicated, right. More flexibility means that the hardware underlying it, the microarchitecture, is going to be more complicated. Okay. So, this is something that you have to keep in your mind. Okay. So, revising what exactly we have, we had memory, then we looked inside the CPU. Number 1, we had a set of registers, and which is called the register file, and I can look up a value of a particular register and load the contents to the arithmetic and logical units for doing some operation, right. So, the ALU stands for arithmetic and logical unit. So, let me mark them. So, this is your register file. Number 2 was the ALU, which is your arithmetic and logical unit. There is no as such definition set in stone that you have to support this number of operations. Again, it is up to you, whoever is designing the CPU. Typically, we do have addition operation, because addition is something which is fundamentally needed for a lot of any sort of reasonable programs, right. Addition, subtraction is typically, we anticipate them to be a part of the ALU, and you might have some logical operations, at least and operation and not operation, right. So, if you have and operation, not operation, which is then you can perform NAND operation, right, which basically tells you anything, any logical expression could be computed, right. So that makes it logically complete, like logical completeness could be achieved, any Boolean expression could be executed. Okay. So, and not let us say addition, subtraction, maybe something more if you want to make the ALU more powerful, let us say you can have multiplication, right. So, that is going to be a part of your ALU, and the ALU also is going to take another input which says that what operation. Okay. So, all of these things how they are connected, do not worry about that right now, I am going to touch upon them. So, the ALU must know whether it is going to do an addition operation or subtraction operation or an AND operation or an OR operation. It has to be told, and the instruction, right, these 4 bits of the instruction is going to contain that information, right. So, whenever it says, whenever it sees let us say 0101 which is 5, it understands it is an add operation, right. So, the ALU is not going to choose or an XOR or a NOT, right, it is going to choose the full adder, right. Whenever it sees let us say 111, 0111 which is 7, maybe the 7 stands for an XOR operation. Whenever I see 0111 here, the ALU, inside the ALU it is going to choose the XOR operation, and if you have A and B which are coming in, so it is going to automatically compute A XOR B. Whenever it sees 0101, right, whenever it sees 00101 which is let us say add, it is going to compute A plus B, right. Whenever it sees let us say 3, okay, 3 could be 0011, 3 could stand for subtraction, it will do A minus B, right. So, the first 4 bits here denotes what is the operation that is going to be executed on the processor, okay, and the rest we are going to define. We might not have this complicated scheme for our CPU design, we are going to restrict ourselves to a much more simpler processor. We may have just 2 or 3 registers, not even 8 registers, okay, and these are the 2 things. The other things, there are several other things which are which require a little bit understanding of the how an instruction is executed. At least one thing I would mention is something which is called a program counter. Okay, so this is a third thing. Third thing is called it's called a program counter. So, as I told you, one instruction we can execute, right. So, if you go back to this particular slide, as you can see, do X is one instruction, and I have explained how one particular instruction is executed, right. Not gone into the details of that, but at least you can have a feeling that this do X, whatever it means, let us say add something, is going to be coming inside the CPU somehow. Some of the values are going to be stored in these registers somehow, and these values are going to be passed on to the ALU. The ALU is going to compute the value and again store that value inside some register, and this value could be passed on to the memory later, right. This is how do X or do Y is executed, right. But when a program executes, it is not one instruction, right. It is going to execute a sequence of instructions, and you have to, somebody have to keep track what particular instruction have been executed till now. Okay. So, suppose this is a program that contains 5 instructions X, Y, Z, W and R, and at every point of time I have to know that how much has been finished. Okay. So, after I do execute do X, right, somebody has to tell me the next time I am going to execute the next instruction, it has to be do Y. After I do Y, it has to go to do Z, right, and so on, unless and until there is some jump or like a function call, something like that, I will keep on executing the instruction sequentially, right. So that is why, as I told, the program is stored in memory and memory is indexed by address, right. So if I think of this particular program is being stored from memory location, let us say 10, right. So 10, 11, 12, 13 and 14, right. So these are the addresses, right. From 10 to 14 there are 5 bytes, and I am assuming that do x or whatever instruction that we are considering may be containing 1 byte, or right. So 10th byte, 11th byte, 12th byte, or 10 is the address of your memory location where my current code is executing. So what does the program counter do? The program counter stores the address of the next instruction that is going to be executed. So suppose it is currently executing do x, right. Whenever do x is done, by that time the program counter contains the value 11, right. So whenever it sees the value 11 in the program counter, do y is going to be executed. But whenever this do y is getting executed, the program counter is updated to 12, right. And then after this do y is done, it is going to check the program counter and see that this value is 12. It is immediately going to transfer the control to load this instruction do z to the CPU and execute that. Okay. So I am going into I am kind of telling you a little bit more superficially. When we see the overall concrete architecture of our CPU, that is what we are going to do next. Next couple of lectures maybe, the idea will become more clear. Okay. So the program counter, you can think of this as a pointer to the instructions that are being executed in the program. At what point of the program currently you are while you are executing. All of you have probably done debug, right. Whenever you are debugging, you set a let us say breakpoint, and then you from that point you are going to go step by step, right. In this particular case, each step is an instruction. You execute one instruction, then you go to the next instruction, you go to the next instruction. Who is going to tell the CPU which instruction to execute comes from the program counter. So this is a very important part of your CPU, which is basically the program counter. It contains the address where you need to where you are basically executing your program. The next instruction that is going to be executed, the value or the address of that instruction is going to be stored in the program counter. And apart from that, there are some special registers which basically figures out like based on the instruction, like suppose I am giving an instruction, again add src1, src2 and so on. These 3 bits that represent the source register, some decoding has to be done, right, because by seeing that address you are going to find out which register is going to be loaded, from which register you are going to read the output, right. Those things you require circuits for that, you require multiplexers, decoders and so on, and of course there will be a lot of use of multiplexers and decoders, right. So this thing has to be, if you are not yet revised them properly, please go back and try to understand what are decoders, multiplexers and so on, and there will be a lot of use of these counters and registers now, right. As you can already see, that program counter is nothing but a counter, right. It is basically an up counter that starts at the location of the address where the program starts, and it keeps on incrementing, right. So you need to load the counter. Suppose your program starts from the memory location 10 as told in this example. So the program counter should be loaded with the value 10, right, or if 10 is in the decimal value, so it should be 1010 for a 4-bit counter. So 101010111100 and then 14, right, 1110. So these values, as you can understand, it is basically an up counter which could be reset, which could be loaded with a particular value, and that is pretty much it, right. And then we also have to understand, revise what is a register. Because as you can see that register is one of the sole things inside a inside the processor, right. So full adders is an essential component of ALU, and of course we cannot do away with logic gates. There are so many different things that are needed in terms of when you try to process an instruction. Logic gates are required to kind of for various processes, right. So we will look into it, right. We cannot really avoid logic gates to build. So various kinds of things like AND, or XOR, NOT, right. This thing should be kind of afresh in your mind. So all we are going to do is stitch together all these different concepts and build a working prototype of a system that we are going to simulate, where we store a program in the memory, and that program get executed, and that program is defined in terms of instructions that we define ourselves, right. The instructions has to be defined by us, and we are going to implement the specific microarchitecture for that instruction set. Okay. I think this is pretty much it. One observation that you need to make here, again this is a high level pitch for the processor, right. We are going to look into the actual details of all these things. As you can see that pretty much all the computation gets done here, right, ALU. Okay. So if you remember, I told in the first slide of this particular topic, right, we spoke about that operation X, which could be an addition operation plus the interfacing circuit. So the entire thing that we are showing here is your interfacing circuit. All that you are trying to do as a part of this addition is just use a full adder, right. That full adder is something that you have already known from your combinational circuit lectures, right. It's very simple. A XOR B XOR C, that does a full addition with a carry is AB plus BC plus CA, right. A and B, you are trying to add these two bits, and C is the carry in, right. And you can do this full adder for like a 4-bit full adder or 8-bit full adder or a 16-bit full adder based on the size of your data. Okay. So conceptually it is very simple. The only problem is that how do you make the interfacing circuit so that this is very generic. Any program could be executed, any instruction set could be executed. So the interfacing circuit becomes a little bit tricky. Okay. The interfacing circuit has to be made very intelligently, or the microarchitecture, which is your interfacing circuit, has to be made intelligently, such that you don't make it like you don't have a lot of redundant circuitry. It is optimized for that instruction set architecture and so on, right. So we will see. So another that observation that I was talking about is, apart from this thing, right, which is your computation, the actual computation, most of the interfacing circuit, as you can understand, is primarily about movement of data. Okay. So I would really highlight this particular fact is, apart from computation, what you have is like I would say plus, right, movement of data. No real computation, right. You are moving from memory to a register in the register file. From that register file you are moving that to the ALU. The ALU does some computation, and then again the data comes to the destination register. The destination register value might have to be saved to the memory block. Most of it, as you will see later also, is about the movement of data, right. So as if you have this huge highway and a processing plant, right, inside a small town, right. So the processing is very simple, that if you reach the processing plant, the processing is very simple. The problem is that there are so much data which are floating around, so you have to orchestrate the how the data moves from the memory to the processing plant, which is your ALU here, and back to the memory, right. And you can have so much data, and you have to kind of make your processing the overall processing very fast, right. The end-to-end latency of the instruction being read from the memory, and whatever value has to be stored back to the memory, this entire time, if you look at this end-to-end time, this has to be kind of taking as less amount of time as possible, right. So, the execution, that instruction execution time has to be reduced. Okay. So, it could be making the microarchitecture very complex. So, for example, you can have a circuit that does multiplication, right. In that case, the instruction is very complex, but it is just a single instruction, right. Whereas you may have a simpler circuit, and the simpler circuit is only going to do addition. Of course, addition will take lesser time, but you have to do many additions to achieve multiplication, right. So, as you can see, there is this lot of uh, data which is actually floating from memory to the ALU and from the ALU back to the memory, and this is the task of the designer, how intelligently you want to design the instruction set architecture as well as the underlying microarchitecture to achieve a latency which is minimal, right. So, that the speed of the processor is increased, right, because ultimately we want to make sure that the programs run fast, right, and in order to make the programs run faster, you need to optimize this thing, right. So, as we will focus of course on the computation, a lot of the focus is also going to be on the data movement side, or how do you make sure that what is the protocol to control the movement of data inside the CPU, right. That is something that is going to be taken up directly after this lecture. Okay. So, remember this overall design that I told you in a very superficial sense. We are going to revisit this again, and we are going to start with thing number 1 or the point number 1, which is movement of data across registers, right. So, register 1 may have to copy the data to register 2, register 2 might have to copy the data to register 4. One quick example is the swap operation. All of you have encountered a swap operation where you want to, let us say, swap the values that are stored in register X and register Y. All of you know that you may require a temporary, you will require a temporary register, right. So, you have to save the value of X in a temporary register, copy that to Y and copy it back, copy back temp to X again, right. So, this requires 3 register operations, right. So, how do you architect the system to have this register operations or register transfer operations possible, and what is a better way or a smarter way to do that inside the CPU? We will start with that. After that, we will look into the overall architecture again, right, that we are going to design, because we have to stick to our instruction set. So, we will define our instruction set and then start kind of finishing up a prototype that can execute programs written using our instruction set. Okay.